Right, so that's giving you, we've looked at how we test chemically for different functional groups. Now we're going to use a different way. How can we give us a little bit more information about what an actual molecule is? So this is all about an unknown organic compound. How can we use spectroscopy to tell us tell us a bit more information about what perhaps we've got? The first one we're going to look at is infrared spectroscopy. So how does this work? Well, we draw molecules. So let's say we're going to draw water, and we draw it like that. Is that a good representation of water? Well, there are many reasons why it's not. First of all, I know that represents an oxygen atom for us, but in reality, if I was to look at an oxygen atom, it wouldn't look like a big O on it. It wouldn't have an O stamped on it. And equally the same for hydrogen, you just see lots of electron clouds. The other big problem is that I've drawn it as a static representation. That's the only way I can draw it on a board. It's just static. However, molecules always move in the whole time. They're moving around. And the main thing is that they vibrate as well. So what's happening with this guy is that these chemical bonds are actually vibrating back and forth like so. And you also see them bending as well. So if I'm a water molecule, that's the oxygen, these are the hydrogens. It's going like that the whole time. It's vibrating, actually it's bending as well. So the two hydrogen atoms are going like that with each other. So it's going vibrating, the bonds, which are my arms, are vibrating like that the whole time. Okay, so how does this work for us? Well, they vibrate at frequencies similar to infrared radiation in the electromagnetic spectrum. So if I can shine infrared radiation at these molecules, and this vibration has a certain frequency in the infrared spectrum, and if I get the right frequency, it vibrates even more and it absorbs the radiation. So that works for us. So what I do is I get my molecule, and this is ethanol here, and I go for all the different frequencies of infrared radiation. To make it easier, I use a different frequency scale. I call it a wave number, and it's in centimeters to the minus one. Don't worry too much about that. It's just a different way of measuring frequency. It gives us nice numbers. Okay, and this is what I would see. So what is this actually telling me? Well, it's telling me that around about 3,300, can you see it's absorbed all that radiation? The molecule took that and went, way, I want that, I'm going to absorb that. So it took that. It didn't really like any of this radiation, and there was a little bit more radiation there, radiation here. So every time this peak comes down, it means the molecule has absorbed it and caused it to vibrate a little bit more. And the good thing for us is that certain bonds vibrate at certain frequencies. So when you look at your data sheet, which I will pop up in a minute, you will see you'll be given a list of frequencies. So let's look at the data sheet. Right, so this is the first page of your data sheet, and it's really important you use this in the exam. So make sure you've got your data sheet first of all in your exam paper, which you will have, and then use it. Okay, so Table A gives you a list of lots of different covalent bonds, which we commonly see in organic molecules, and it tells me the frequency that they absorb at. So an NH bond absorbs between 3,300 and 3,500 wave numbers. An OH bond absorbs between 3,230 and 3,550 wave numbers. Now, I'm not going to go through all of these, but hopefully you can see they're all quite spread out across the frequencies that we use. So what I can do is when I see one of those big dips, I can just look and see where was that dip, look at the frequency, check against this, and that will tell me the bond that I've got. So if, say, I absorbed a massive frequency at around about 1720, which we maybe see a little bit later on, I go, woo, 1720. Oh, 1720 is between these boys, so it looks like I've got a C double bond O bond in that, which means it's perhaps an aldehyde, a ketone, or a carboxylic acid I've got. If it was a carboxylic acid, what else would I see? Well, I'd also see an OH bond. So if I saw an OH bond, and it was a really broad one, look at that. That's got a frequency range of 500 wave numbers. That's going to be really broad. If I saw that, and so if I saw that one and I saw that one, so those two, you would know you've got a carboxylic acid. If you didn't see that one, you only saw that one, then you'd be thinking, oh, maybe I've got an aldehyde or a ketone. And it gives you clues as to what functional groups you've got in your molecule, which is really handy. Right, so let's go back to this spectrum. So this is the infrared spectrum of ethanol. So if you didn't know what molecule it was, what could you tell? Well, you could see I've got this broad absorption here, and that is an OA, a OH bond in here. I haven't got a lot going on here, but I've also got this strong absorption here at around about 1,000, which is a CO bond there. Probably the most useless absorption is a CH bond. CH also absorb around here, but CH you kind of see a little bit like that if it was a CH bond. Pretty much every organic molecule has a CH bond, so it's not particularly useful for us to actually quote that. The ones you want to quote are things like OH and C, O bond, C double bond, O bond, things like that. Things that actually tell you about the functional groups. And the thing to do is quote the range that you see in your spectrum and then cross-reference it against the range that is quoted on your data sheet. So use what you see on your spectrum and what you expect from your data sheet, and therefore you've got this type of bond in it. So use both the bits, both the numbers in any answer that you give in the exam. The other thing to be aware of is you have a fingerprint region of the infrared spectrum. The fingerprint region, which is around the bottom end of the spectrum, every organic molecule has a unique fingerprint region. Everyone will have a unique infrared spectrum. So what we have is we have a database of all the infrared spectra of lots and lots of different types of organic molecule. What you can do is if you had an unknown compound that perhaps you've made, you could do the IR spectrum of it, upload it. The computer would then cross-reference against all the different spectra that it holds in its database, and it would tell you the exact molecule it's got. So it's a bit like us. We've got unique fingerprint that identifies us. The infrared spectrum is unique for every organic molecule, so that will be able to identify it against that.